All right, let's jump right in. We're going to unpack a concept that is, no exaggeration, a cornerstone of electrical engineering. It's a brilliant mathematical trick that not only keeps our power grid safe, but it's one of the main reasons we could even build such a massive interconnected grid to begin with. We're talking about how you bring order to complete and utter chaos.
It seems like it should be a simple question, right? A tree branch falls and knocks down a power line. It feels like it should be pretty straightforward to figure out what happens next. But in a three-phase power system, that one singular event creates a massive analytical headache, and it can threaten the stability of the entire network.
So here's the deal. When a power system is running smoothly, we say it's balanced. That means the voltage and current in all three phases are perfectly equal, just separated by a moment in time. This beautiful harmony lets engineers look at just one phase to understand the whole system. But the second a fault happens, that balance is shattered. The phases become wildly unequal, and all those simple analytical tools, well, they just don't work anymore. It's like trying to solve a puzzle where none of the pieces fit. And here's the kicker. This messy, unbalanced state isn't some rare exception. It's the rule. The vast majority of real-world faults are what we call unsymmetrical. We're talking about everything from a single power line touching the ground to two lines smacking into each other. This is the stuff our grid deals with every single day, and for a very long time, calculating the effects was incredibly difficult.
But then, over a century ago, there was this breakthrough. A totally new way of thinking came along that allowed engineers to tackle these chaotic, unbalanced problems with this unexpected elegance and precision. The idea came from an engineer named Charles Legay Fortescue. He presented a paper that would fundamentally change power system analysis forever. He introduced a method that is still one of the most powerful tools in an electrical engineer's toolbox today. He called his method symmetrical components. Now, I know, the definition sounds a little dense, but the idea at its core is pure genius. It's basically a mathematical transformation. You take a messy, unbalanced set of currents or voltages, and you break them down into three separate, perfectly balanced systems.
Think of it like this. An unbalanced fault is like a jarring, dissonant musical chord. It's just noise, and you can't easily analyze it. What Fortescue's method does is deconstruct that ugly chord into three pure, simple, perfectly balanced notes. And by analyzing those three simple notes one by one, we can completely understand the original complex mess. That's the power of symmetrical components.
So what are these three pure notes, these perfectly balanced sets? In the world of engineering, we call them sequence components. So let's meet them.
First up, you've got the positive sequence. This is easy. It just represents the normal, healthy, balanced operation of the power system. Then there's the negative sequence. This is also a balanced system, but it spins in the opposite direction. It only ever shows up during unbalanced faults, and it's really bad news for rotating machines like motors and generators. And finally, you've got the zero sequence. This one's a bit weird. It's a set where all three components are actually identical. And these currents can only flow if there's a path to the ground, which makes them super important for analyzing the most common kinds of faults.
Now, this visual really helps make sense of it. You can see the positive sequence spinning in its normal ABC order, but then look at the negative sequence. It's also perfectly balanced, but it rotates in the opposite ACB direction. And that difference in rotation, it isn't just some math curiosity. It has real, physical, and often damaging effects on power system equipment.
Okay, so we have this powerful theory, but how do we actually use it to calculate fault currents and, protect the grid? Well, that's where the concept of sequence networks comes into play.
This right here is the practical magic of the method. We can literally create a separate, simple, single-phase circuit diagram for each of our three sequences, the positive, negative, and zero. The incredible advantage is that these three circuits are totally uncoupled from each other. We can analyze each one completely on its own, which turns an impossible problem into three much more manageable ones. And this diagram just perfectly illustrates what those networks look like. Instead of one impossibly complex three-phase diagram, we get these three clean, separate single-phase circuits, one for positive, one for negative, and one for zero. It is a massive simplification that makes the calculations totally feasible.
So we've got our three simple networks. Now, how do we use them to simulate a specific fault, like that tree branch hitting a single line we talked about earlier?
This is the final, crucial piece of the puzzle. To model a specific, unbalanced fault, we just connect our three sequence networks together in a specific way right at the point where the fault happened. A single line-to-ground fault has one connection pattern. A line-to-line fault has another.
The way we connect them is the model of what's physically happening out there on the power line.
So the whole process, which of course is now done in a split second by computers, follows these logical steps. First, it builds the models for the 3 separate sequence networks. Second, it defines the fault, which tells the program exactly how to connect those networks together. Third, it solves for all the currents and voltages inside that simplified sequence world. And finally, and this is key, it uses a reverse transformation to convert those simple sequence values back into the real-world phase currents that are going to flow through the grid during the fault.
Okay, let's just step back for a second and appreciate why this method hasn't just survived for over a century, but why it's still the absolute gold standard for this kind of work.
The advantages are just immense. First off, it takes a tangled web of equations and turns it into 3 clean, separate ones. But it's so much more than just making the math easier. This simplification is what makes it possible for computers to analyze huge, complex power grids almost instantly. And most importantly, the results from these calculations tell engineers exactly how big a circuit breaker needs to be, or how to set a protective relay so it trips in a millisecond to stop a small problem from causing a massive blackout. It is the fundamental tool of grid protection. For over 100 years, Fortescue's method has been the bedrock of fault analysis. Its elegance and its power have made it an indispensable tool that has absolutely stood the test of time.
And that really leaves us with a final thought to chew on. Our electrical grid is more complex and more critical than it has ever been. Without a tool to make its chaotic, daily faults understandable, building it to this scale would have been practically impossible. So the next time your lights flicker for a second and then come right back on, you can probably thank the elegant, century-old idea that brought order to chaos.